here's the definition of homomorphism. Suppose we have two rings, R and S. And let F be a mapping from R to S such that f of x plus y, and x and y are of course elements of R, is equal to f of x plus f of y. And also f of x times y is equal to f of x times f of y. Then this mapping F is a homomorphism. Homomorphism from R to S. Or we can say also say ring homomorphism. Homomorphism. Okay. So be careful. This addition here is the addition within R. Okay, within R. Oops. Addition in R, and this multiplication is also multiplication in R. The addition here on the right hand side is the addition in S, and multiplication on the right hand side is the multiplication in S. So this addition, these additions and these multiplications, they are defined on different rings. So just like the case for groups, the ring homomorphisms are mappings that preserve the structure of rings. Okay, so addition to addition and multiplication to multiplication, and we will see more structures are actually preserved by homomorphisms. Let's see an example. Let's say n is any natural number, and let us define a mapping f from integers to the remainders of integers when divided by n. This f is defined like this. So f of a maps integer a to the congruence class of a. Okay, then we can see that this mapping is actually a ring homomorphism. In fact, the congruence class of a plus b is the sum of the congruence class of a and the congruence class of b. And the congruence class of AB, so the product of the is the product of the congruence classes, as we have defined before. So this mapping preserves addition and multiplication. And here's another example. Consider the set of polynomials in X over a field F. Okay, and F is a field. And let alpha be any constant of that field. Then let's define a function from the polynomial ring to the field F by f of a of x. A of x is a polynomial of x, so this maps to a of alpha. Okay, then this f is a homomorphism. So as we can easily check, a x plus bx, if this is equal to c cx, c of x, and a of x, b of x. If we define c and d like this, then a of alpha plus b of alpha is of course c of alpha, and a of alpha times b of alpha is of course equal to d of alpha. So the result of, so if we apply this mapping f to the both hands of these equations, then we have this. So the addition is preserved and the multiplication is preserved. The next theorem showed some of the important properties of ring homomorphisms. And let's say we have a homomorphism f from R to S. Of course, R and S are rings. Okay, and we have first, if all R and all S are, let's say, if are zero elements of R and S respectively, then we have f of all R is equal to Rs. So that means the zero element is mapped to the zero element by a homomorphism. Okay, let's see, homomorphism. And second, for all x in R, we have negative f of x is equal to f of negative x. Of course, negative x means the additive inverse of x, and negative f of x is the additive inverse of f of x. Okay, and 3, R is f of R, so the image of f is a subring of S. And 4, if we set K equal to a subset of R such that its image is the zero element of S. Okay, then K is an ideal of R. Okay, so this looks familiar maybe. This is actually called the kernel of this mapping F. So let's prove this. And out of these 4 points, the point 1 and point 2, they are almost trivial because they are only dealing with additive properties of the rings. Okay, so this ring homomorphism can be considered as a group homomorphism with respect to the additive operation. Therefore, this is true and this is true. So these are okay. And furthermore, about this image of R by F, we can see, so 1 and 2 are done, and 3, f of R is a additive subgroup, an additive subgroup of S. No, ring homomorphism is a group homomorphism with respect to the addition, so this is okay. And to show that this is indeed a subring, we need to show the closure condition for the multiplication. But that is also easy to show because this F is assumed to be a homomorphism, so the multiplication is preserved. Okay, so that means if, let's see, if y1 and y2 are elements of f of r, then y1 then that means then there exists x1 and x2 in R such that f of x1 is equal to y1 and f of x2 is equal to y2. So y1 times y2 is equal to f of x1 and f of x2, but since f is assumed to be a homomorphism, this is equal to f of x1 times x2. And of course, this is an element of f of r. So therefore, f of r is closed under multiplication. So according to the subring criterion, this is a subring of S. And for part 4, as we have mentioned, this is the kernel of this mapping F. If we regard this as a group homomorphism. Okay, so we already know, so this is the kernel of the group homomorphism. F with respect to addition. Therefore, K is an additive subgroup of R. So this is already proved for groups, so we just take it for granted here. And then we show that for any element of R and any element A of K, we show XA is an element of K. Okay, so let's, we want to show this. So and f of xa, since f is a ring homomorphism, this is f of x times f of a. And since a is an element of the kernel, this maps to 0 element of S. But 0 element times any element is a 0 element. Therefore, XA belongs to the this K. And similarly, we can also show that AX is equal to OS or times f of x, which is OS. Therefore, AX is in K. Therefore, K is an ideal. So it's two-sided ideal of R. And we are done. So we extend the definition of the kernel of a mapping to ring homomorphism. So this K is called the kernel of F, and we write as this ker F. So kernel of F. Now we are going to prove various results that are analogous to those of group theory. First of all, if we have a ring, ring, and an ideal of the ring, then by definition, an ideal is an additive subgroup of this ring. Okay, so based on this ideal, we can define cosets. So for any element x of the ring R, we can define x plus I. So this is a coset of I containing x. Oh, it's not I, it's A. So this is a coset of I. So let's review this lemma we have proved for groups. Okay, so if we have a ring homomorphism from ring R to ring S, and such that K is the kernel of F, and then let X and Y be elements of R, and then F of X is equal to F of Y if and only if the cosets of K are the same. So we already proved this lemma for general groups. So in this lemma we are just using the property of these rings as additive subgroups, additive groups. So this still holds. So we skip the proof and move on to the next theorem. And again, R is a ring and I is an ideal of R. And let R over I be the set of cosets of I. And we define addition and multiplication as follows. Addition and multiplication. So x and y are elements of R. So x plus I is a coset of I containing x, and we define addition. So addition between two cosets. So we define this addition by this. So if we add these two cosets, then we get this coset. Okay, x plus y is an element of R. So the result of this addition, we define it to be the coset containing the element x plus y. And also we define multiplication, x plus I times y plus I by xy plus I. So this is another coset. Okay, so let's define these, and then these operations are well defined. And under these operations, R by I is a ring. And furthermore, the mapping from R to R by I by mapping x, each element x to x plus I is a homomorphism. So this is a homomorphism. From R to R by I. And the kernel, let's with kernel I. So this ideal is the kernel of this mapping. Okay, let's prove this. But ring is an additive group. So as far as addition is concerned, we already know that R by I is an additive group. So we need to show, so this is okay. Addition is okay. We already proved it before. So we need to check whether the multiplication is well defined. So by the way, so what this means is that if x plus I is equal to x prime plus I, and y plus I is equal to y prime plus I. So if we choose different representatives of the same coset, do we still get the same results for the multiplication? So that's the question. So if this is the case, then x, y plus I is equal to x prime, y prime plus I. So is this true? This is what we need to show. By the way, to show this, we need to show that xy minus x prime y prime is an element of I. So this statement and this statement and this statement are equivalent, as we have seen in a previous chapter. So let's try to show this. So suppose x plus I is equal to x prime plus I, and y plus I is equal to y prime plus I. So in this case, then this means x minus x, let's say x prime is equal to x plus A, and y prime is equal to y plus B, where A, B are elements of this ideal. So x prime times y prime is x plus A and y plus B. If we expand, we have xy and xb and ay and ab. Okay, and since I is an ideal, this means two-sided ideal. So this. So A, B, they are both elements of the ideal. So all these elements are elements of the ideal I. So therefore, x prime, y prime minus xy is an element of ideal. Therefore, xy plus I is equal to x prime, y prime plus I. Therefore, uh, the multiplication is well defined. And we already know that R by R is an additive group. And we need to show, in order to show that this is a ring, we need to show that this is a multiplicative semigroup, right? So let's show that. And we know that the multiplication is closed. We just show that multiplication is well defined, so that's okay. And the remaining thing to show is that the associativity of multiplication. So let's show that. X plus I, y plus I. So if we multiply these first, z plus I. So what we get here is, so first do this, then that will be x plus x times y plus I, and z plus I, and that is xy z plus I. But xyz, this multiplication is associative because R is a ring. So we have x times y z plus I. So that is x plus I, y z plus I, and y plus I times z plus I. So the associativity holds. Associative. Okay, therefore R is a ring. Oh well, we actually need to prove distributive laws, but I think it's easy enough, so I will skip it. And anyway, so we define the mapping f by x plus I, where x is an element of the ring R. So this is a group homomorphism already. So preserving addition. Okay, and to see if it preserves also multiplication, we show check f of xy. So by definition, this is xy plus I, but by the definition of multiplication between two cosets, this is equal to x plus I times y plus I, but these are the results of f of x and f of y. So therefore, f is a ring homomorphism. And finally, we need to show the kernel of this homomorphism is the ideal I itself. So the kernel of f is defined to be those elements of R such that that are mapped to the identity element. Okay, so identity means additive identity, so that means zero elements, so 0 plus I in this case. Okay, so this is just equal to I. So, but by the definition of this mapping F, this is x plus I. So if this is equal to I, then so if these two sets are equal, then this means this set itself is I. So we are done. Let's see an example. So we already seen that this is a ring. The set of integers is a ring. And the set of integers that are multiples of n is an ideal of z. So so z over nz, which was defined to be zn, is a ring according to the previous theorem. And also, just like for the case of group homomorphism, if F is a ring homomorphism, then if F is also injective, then we say it's a monomorphism. Monomorphism. And in addition, if it is a surjective homomorphism, then we say epimorphism. So the same terminology as group homomorphism. And if it is bijective, we say isomorphism. Okay. So just like group homomorphisms. And if we have a homomorphism from R to S, which is an isomorphism, So if there exists a homomorphism from R to S that is an isomorphism, then we say R and S are isomorphic. Morphic to each other. Or we could write R is isomorphic to S.